Hello. After discussing flow control and congestion control, in this lecture we shall start our discussion on one of the most complex and crucial function performed by the packet switching nodes known as routing. What is the purpose of routing? As you know, in a packet switching network, you have a number of nodes and a number of stations are communicating through this network of nodes. A packet is introduced by a station which has to be delivered to the destination, and that is the role or job of the routing. Let us have a look at this example packet switching network where you have got 6 nodes which are packet switching nodes, and obviously there are stations connected to it. Say A is connected to node 1, 6 is connected to node 6 is connecting station 2, station B, and so on. Now, to send a packet from A to B, A sends it to the node to which it is attached. From A to B, the packet has to go through a number of nodes using multiple hops. Now, if you look at this simple packet switch network, you will find that there exist multiple paths. For example, it can go through this route 1, 2, 3, 6, and then B, or it can go through 1, 4, 3, 6, or it can go through 1, 2, 4, 5, 6, and so on. So there exist multiple paths. Question is, which path is optimum? Which path gives you least cost? Which path is economical? That has to be decided by routing. Now, one point you must understand: if you look at a particular node, when a packet is introduced, its role is to transmit it to one of the outgoing links, and similarly, as it reaches the other node, after receiving it, it will transmit it through one of the outgoing links. That means the nodes receive packets through its incoming links and transmits them through outgoing links. The routing function decides to which outgoing link a packet has to be transmitted. Now, in a routing function, there are various requirements. We shall discuss these requirements first before we consider different elements of these routing techniques. Number 1 is correctness. Correctness is self-explanatory. It means that if station A wants to send it to station B, that packet has to be delivered to B. That is the correctness. That means it should be delivered to the proper destination. Simplicity. the algorithm of the routing function should be simple so that it can be easily implemented. The software overhead is small. As you know, this routing function is a software is implemented by a software which is part of the network layer. Third important requirement is robustness. By robustness we mean in a network, in a packet switch network, we have seen some of the links may fail, congestion may develop in some parts of the network, and as a consequence, because of link failure, because of congestion in some part of the network, a packet may not get delivered in time, may take enormous time, unbounded time. The algorithm has to take care of this situation. If the algorithm can take care of these situations, it is robust. Then stability. By stability we mean the routing function should be stable. Some of the parameters are dynamically changing with time, and because of these changing parameters, say congestion, link failure and various other things, what can happen, suppose a congestion has developed in this part of the network at a particular instant. If the algorithm reacts very quickly, what it will do, it will immediately send it to the other part of the network where congestion is less. Then what can happen, the other part will get from the congested node, congested region, it is being diverted to some other part. If it is diverted quickly, it has some advantages and disadvantages. If the switching, that means if the diversion takes slowly, what can happen, by the time it is the path, separate path is followed, the congestion may be the part which was congested make it recover from congestion. So you have to optimize so that you get optimum performance, and this robustness and stability are sometimes conflicting in nature, and you have to use some trade-off, how much robustness you want at the cost of what amount of stability. Then comes the question of fairness. The network ideally should be very fair to each of the stations which are connected to the network. Now, it may so happen that because of various other criteria, a particular node decides that instead of sending to a distant node, let it be sent to the nearest node because of cost criteria. What can happen by this process? You are essentially being unfair to the node which is far apart. So that kind of thing can happen, and so you have to optimize between fairness and optimality. Sometimes to achieve optimality, to send packet at a optimum cost or in an efficient manner, you may have to compromise so far as fairness is concerned. Finally, you have the efficiency. How efficiently the algorithm is working. Is it very efficient or overhead is very small? So all these things are decided, are some of the requirements of a routing algorithm. Obviously, we have to look at various elements of the routing function before we consider how the algorithm is implemented. Let us see what are the different elements. Elements of routing functions. First of all is performance criteria. Performance criteria. What kind of performance criteria you will use in an algorithm? There are several alternatives. One is, say, number of hops. For example, if you use this path, then the number of hops is 1, 2, 3 and 4. Or you can say number of, if you don't consider this one, you have to make 1 hop, 2 hop and 3 hop. On the other hand, if you use this path, then the number of hops required will be 1 and 2. So the number of hops can be one of the performance criteria. Other possibility is cost. Cost is usually related to, inversely related to data rate. You want that the cost should be minimum. That means higher the cost, lower will be the data rate, and lower the cost, higher will be the data rate. Second is your delay. In some paths, there may be queuing delay. As you have seen, a packet switch network is nothing but a queue of packets, network of queues, and because of this there will be variable amount of delay through different paths. So which particular path gives you minimum delay can be one of the performance criteria. And finally, throughput. Throughput means what is the, by using a particular algorithm, when you are able to get maximum number of packets delivered, that is the throughput. The number of packets that gets delivered in a network is the throughput, and which particular technique gives you maximum throughput, that can be one of the criteria or designing the packet switching, the routing algorithm in packet switching network. Then comes your decision time. When this routing decision is taken, there are two alternatives. It can be packet, that is true in case of datagram type of network, datagram type of service. That means each packet is independently routed. Routing decision is taken independently for each of the packets. So packet is the decision time. When a packet comes, a decision is taken through which route it has to be routed. On the other hand, it can be based on session. When in the beginning of a session, which is in case of virtual circuit type of service, what can happen in the beginning of the session, you are establishing a virtual circuit, and once the virtual circuit is established, as you know, all the packets of that particular message will be sent through the same path. So here the decision time is the beginning of the session. On the other hand, in the first case, in the datagram type of service, each packet is independently decided. So packet decision time is packet. Now it can, where the decision is being taking place. So decision place. There are several alternatives in this. For example, it can be each node. In datagram type of service, as you know, as the packet is passing through the network, each node has to decide through which that packet has to be routed. So each node is provided with the routing capability, and decision is taking place in each node. Or it can be, say, central, there can be a central node which decides the routing techniques. And in a centralized algorithm where one particular node will decide how the routing will take place. That routing algorithm is performed in a node, and that from that node the routing algorithm is decided, and accordingly routing is done. And in this particular technique there is some problem. This is prone to failure. If that central node fails, then routing will suffer. A particular part of the node can become inoperative. It will not remain functional. So this is prone to failure. On the other hand, when it is each node, it is distributed. It is much more robust. And there is another possibility, it is decided by the originating node. That means when a packet is introduced by a station, the originating node incorporates the information about routing. So this is known as source routing. So these are the three possible alternatives, and these decision time and decision place, they are interlinked in the sense that depending on whether it is datagram type or it is session type which is used in virtual circuit, the decision place will also change. Let us see the other elements. The other elements are network information source. That means based on what information that routing is taking place. There are several approaches. It can be based on none. The routing information can be topology, cost of different links, the delay through each link, and so on. In some situation we shall see none of this information is used to take decision about routing. We shall give examples later on, like flooding, fixed routing, where none of these techniques are used. Flooding and random routing, where the network, none of the information about the network is used in deciding the routing function. Or it can be local. The routing decision is taken based on local information. It can be the cost of the links to which a particular node is connected. For example, the decision can be taken by this node based on the cost of these links. So it is local to this particular node. And depending on, for example, it has received a packet through this node, and it has to transmit either through this or through this. It finds that this node has lower cost than the other one, so it will forward through this. So this is based on this local cost. Or it can be one of the adjacent node. What can happen, instead of based on links, this particular node can gather information from its neighbors, the adjacent nodes, to find out whether there is congestion in that part of the network in these nodes, or what is the queue length in each of these nodes, and based on that the decision can be taken. So this is the information algorithm in which information is taken from adjacent nodes, or it can be nodes along the network, along the route. What can happen, say this particular node forwards it to this, then each node takes information from this route. As it sends from 1 to 2, some information is passed on, from 2 to 3 and some other information, additional information is passed on. In this way, as it traverses, in each node the along the route the information is gathered and accordingly decision is taken. Or it can be based on all nodes, which is a global algorithm in the sense, instead of considering the adjacent links, adjacent nodes, or each of these nodes as it passes on, it can be based on the complete information. Complete information means what is the topology, how they are connected, what is the cost of each of these links, where, how much delay is there, how much queue length is there in each of these nodes. Or it can be based on, say, what is the, in which part congestion has occurred. So it is a much more global approach in which the information is gathered from all nodes. Finally, another element is network information update timing. It can be continuous. When it is taken from, say, local nodes or adjacent nodes, it can be continuous. Each node continuously gathers information from the adjacent nodes or from the links to which it is connected, and accordingly it takes decision continuously. Or it can be periodic. At some regular interval, it gathers information maybe from all nodes, and then it takes the decision. Or it can be whenever some major change takes place in the network. Say there is change in topology in the network. In such a situation, only in that situation it will gather and update the timings. Otherwise, it will follow the previous one. Whenever some major change, like change in topology and various other things, or say major load change, suddenly the load is increased. In such situation also there will be need to change the routing. So these two, the network information source and network information update timing, these two are also interrelated in the sense, whenever it is local it can be continuous, but when it is more global involving many nodes or all the nodes, it has to be periodic. On the other hand, if it is static, then only when major changes take place in the topology or major change in load change takes place, then it can be done. Let us now consider some of the routing approaches. What are the various routing techniques? One could be fixed routing. There are four basic approaches we shall consider: fixed routing, then flooding, random routing, or it can be adaptive routing. Let us consider these techniques one after the other. First we shall consider the fixed routing. In fixed routing, the routes are always fixed. Unless there is change in topology or some other thing. That means fixed routing is used based on the topology or fixed information, which does not change quickly. That means these routing techniques cannot be based on the flow or the way the packets are sent. It has to be based on topology or something which is static. And in this particular case, the routing approach will be same for both datagram or virtual circuit. And because of this fixed routing, it suffers from lack of flexibility. Whenever there is some link failure or a congestion develops, this fixed routing cannot recover from that situation, because routing decision is taken in the beginning and it does not change because of the changing situations. That's why it is neither robust nor and also it suffers from lack of flexibility. Let us consider a fixed routing technique, how it works. What can be done? Let's assume this is the network, packet switching network that we have already shown you in a bigger form, where you have got 6 nodes, and the 6 nodes are interconnected in some pattern which is called the topology of the network, and different stations are connected to it. Some of the nodes are connected to some of the in addition to the nodes, they are also connected to some stations, as we have already mentioned. Now, what can be done? A table is created which is called central routing directory, that can be kept in some network control center, and using that the routing can be done. For example, station A wants to send a packet to destination node B, which is attached to node 6. Now, how this table will be utilized? Say from node A, node 1, it has to go to node 6 to which this particular station is connected. That information is known in the station. So when this packet is received by node A, since it knows that the station B is connected to node 6, it looks at the directory, it finds that 4. That means it has to forward the packet through this outgoing link. So it will go to 4. And whenever it goes to 4, it finds out, since the destination node is 6, it finds out what is the outgoing link to which it will forward. It finds that 5 is written there. So that means first it is 1 to 4, so it is based on this. Then from 4 to 5, this table is looked up. So it forwards it to 5, and from 5 it gets forwarded to 6 through this link. And that's how it gets delivered. Now, there is no need to keep this entire table if it works in a distributed manner. what can be done? A part of this table can be stored in each of these different nodes. For example, node 1 can keep this small directory, and here the destination node is given. To means to where the packet has to be sent, the destination nodes, and the next node to where it has to be forwarded is mentioned here. It is same as this part. That means a part of this central routing directory can be kept in each of these nodes, and whenever a packet comes, depending on the destination node, it can easily forward to the next node by looking at this directory. So there is no need to keep a big directory in each of these nodes. A small such directory can be maintained in each of these nodes. This is the small directory for node 1, this is the directory for node 2, similarly for node 3, along with this has to be stored in node 4, this has to be stored, node 5, this has to be stored, node 5, node 6, this has to be stored, and so on. This is how it will work. You may be asking how this table is obtained. This can be obtained by using some suitable algorithm based on least cost that we shall discuss. But before that, let me discuss what are the alternatives possible. In this case, we find that it is very disadvantageous. Disadvantageous because it suffers from lack of flexibility. If one link fails, then it cannot work. What can be done? Some flexibility can be incorporated by providing some alternate route. For example, what can be done in addition to, in this table, in addition to when it has to be forwarded to 6, you can find out another path which gives you little higher cost than the least cost. Then information about that can also be kept here. Whenever the forwarding cannot be done through this, then at the other nodes an alternative routing table can be used. So this much flexibility can be incorporated. Let us consider the least cost algorithm which can be used for the purpose of making that routing table. There are two basic approaches. One is known as forward, that is one is based on Dijkstra's algorithm. Let me give you the basic approaches. The algorithms are variation of one of the two basic algorithms. One is known as Dijkstra's algorithm. Another is known as the Bellman-Ford algorithm. This Dijkstra's algorithm is based on forward search. On the other hand, Bellman-Ford's algorithm is based on backward search. And all the algorithms that are being used nowadays are some variation of one of the two algorithms. So let me discuss in little detail this Dijkstra's algorithm, and I shall briefly mention about Bellman-Ford's algorithm. Basic concept or basic idea behind Dijkstra's algorithm is find the shortest path from a given source node to all other nodes. So in this case, a source node is given, and from that source node, shortest path is found out to all other nodes. And the algorithm proceeds in stages. It is an iterative algorithm. It proceeds in stages. In a particular, say in stage K, it will incorporate all the nodes which are away from the source node by K. So in the next iteration, it will add another node into the list, and in this way it will proceed. Let me give you the details of the algorithm quickly. Here we are defining capital N is a set of nodes in the network. In our example, we have 6 nodes, and S is the source node. M is the set of nodes which have been already incorporated at a particular stage of the algorithm. Since it is proceeding iteratively, it will initiate with only the source node, and gradually this M will be built up. And Dij is the link cost from node I to node j. Dii, that means the cost for sending to self, is 0, and Dij is infinity if a particular node, if I and j, these two nodes are not connected. On the other hand, for example, in this case, cost of sending from 1 to 1 is 0. Cost whenever the Dij for 1 to 6 will be infinity because they are not directly connected. On the other hand, cost for sending from 1 to 4 is 1, or from 4 to 1 is 7, as it is given here. So whenever they are connected, Dig is greater than 1, greater than 0, some value greater than 0. Now, and Dn is the cost of the least cost path from node S to node N, Dn, at this stage. So this Dn keeps on changing as the algorithm passes through different stages of the iteration, and ultimately you get the least cost. At a particular instant, the cost will be decided by is equal to Dn. This algorithm has 3 steps, 3 basic steps. Initialize. In this step, the M, the set of nodes, is initialized only by the source node, and Dn is equal to Dsn for n not connected to source. That means if n is not equal to s, then Dn, capital Dn, is equal to Dsn. Now, after this initialization, it finds the neighboring nodes not in M that has least cost path from the node S, and incorporate that node in M. And it finds out W, which is part of M, such that dW is equal to minimum of dj for j is equal to m, and find out the minimum cost, and that is being added to m. That particular node is added to m, and then update the least cost paths, which is dn is equal to minimum of dn or dw plus capital small d wn. That means if the previous path, this is the previous path already existing, whether this is minimum or after concatenating, adding that new node, the cost is less. If this cost is less, this is added, and this is done for all n is equal to m. So in this way, after capital N iterations, we shall be finding the solution. Let us see for our example problem how it proceeds. In iteration 1, m is equal to 1, that the list of nodes is 1, and from D2, I believe if I show you this particular diagram, it will be clear to you. Then 2 is directly connected, so if 1 to 2 is the path and cost is 2, that is being added here. For node 3, D3, the cost is 5 as you can see, and so root is 1, 3. For 4, it is also connected, cost is 1, and D5 is not directly connected to it, so cost is infinity and path is nil. Similarly for D6. Now as you go to the second iteration, a node 4 is added to it. After adding 4, this path does not change, but as you can see, for sending to 3, earlier the cost was 5. Now if you, after concatenating 4 through this path 1, 4 and 3, the cost is 1 plus 3, so it is 4. So path is 1, 4, 3 and cost is 4, and this does not change. And here also, after adding 4, we find there is a path to 5. So 1, 4, 5, there is a path, and cost at present is 1 plus 1, 2. So far there is no path up to 6. So in this way we keep on adding. In stage 3, iteration 3, we add 4, and this does not change, this does not change, this does not change, this also does not change. After adding in iteration 4, after adding 5, this does not change, but this gets changed. For example, for sending to 3, we find a cheaper path, say 1, 1 plus 1 plus 1. So now the cost is 3. As you can see here, cost is 3 through path 1, 4, 5, 3. This does not change. Here also it does not change. And now we have got path for this, for 4, for 6 through this path after adding 5. So in this way it proceeds, and ultimately we get a complete path for all the nodes. As you can see, from 1 to 2, path is 1, 2. For 3 it is 1, 4, 5, 3. For 4 it is 1, 4. For 5 is 1, 4, 5. That is the least cost path. For 6 it is 1, 4, 5, 6. And from this you can easily make this table, which I have already shown. So using this algorithm, you can build up this table. This is, in fact, if we take it, we shall get this table. So in this way, by using this Dijkstra's algorithm, the least cost path can be obtained. And this particular algorithm is based on forward search. We are starting from a source node and going towards a destination node. And it has been found that it is suitable for centralized routing. The reason for that is you require a global picture. You have to know the information about the topology, cost of all the paths to decide the which to at different stages of the iteration. And that's why it is suitable for centralized routing. On the other hand, the Bellman-Ford algorithm, which actually is based on destination, which starts from destination towards different nodes, and this has been found to be suitable for distributed routing. And it has been found that both these algorithms converge under static conditions of topology and link costs and gives the same solution. So in this lecture we have discussed the basic concepts of routing, different elements of routing, and considered the fixed routing technique, how fixed routing technique can be used. And we have also discussed how the table which is being used in fixed routing can be created by using some algorithm like Dijkstra's algorithm or Bellman-Ford algorithm. In the next lecture, we shall continue our discussion on routing and consider other techniques. Thank you.